we got to pick up where we left off last week. Just a brief resume that fully resistive circuits give us current green, voltage red, in phase with each other. Yeah. Then we looked at purely inductive circuit, which is not achievable in real life because an inductor is a coil of wire that's going to have some resistance. There's this imaginary per inductor would give us current and voltage that are out of phase with each other. In fact, the current IL in green lags the voltage VL in red. Yeah. Equally, you could say the voltage leads the current. So either way round would be fine. Okay. So we end up with a phasor diagram where our current and voltage are 90 degrees out of phase with each other. We also took a quick look at how you can check whether current or voltage should be leading or lagging, and that's the word civil. So the way we use that in a capacitive circuit, current is before voltage, so we say current leads voltage. Equally, we could say voltage lags current. In an inductive circuit, designated by the L, voltage leads current, or equally, we just say current lags voltage. Okay? Yeah. All of this is already on the site, and we went through it last week. I'm just trying to briefly hook into what I want to do today. All right. And then we had a look at purely capacitive circuit. Again, not really achievable because there's going to be some resistance in any circuit. But in that, we get a current that leads the voltage by 90 degrees. So this time, the peak of the current is ahead of the peak of the voltage, so it's leading. All right? So, what I want to do now is look at what would designate real circuits, and that's where we might have, we take into account the resistance of the inductor, or we've got some series resistance. So we've got R in series with an inductor L. So, if we take the current as being, the current in a series circuit is the same for both components. So I've got that in red there as being the current that flows in that circuit, and the resistor voltage ER is in phase with it, because we know that current and voltage for a resistance are always in phase. And then the voltage due to the inductor, which I'm going to rewrite here in green, is 90 degrees ahead of the voltage for the resistor. Yeah, and that's also ahead of the current. Does that check out with civil? We've got an inductive circuit, and we're saying voltage leads the current. Inductive circuit, voltage leads current. Yeah. So we've applied the per resistance rule to the resistor, voltage and current in phase. We've applied the per inductor, voltage is 90 degrees ahead. Okay. Our resultant phasor, so the total voltage, i.e. here, is, in a real circuit, is a coming together of those two phasors up the middle. That would be your applied voltage in this case. Yep. So, or the resultant. So we've got a triangle there where this is the total voltage, this is EL, That's ER, and that's the angle. Alright? So that's a phasor diagram for a triangle to express the voltages. What we can also have is a similar triangle to express the impedances. Where we have R, the in-phase part, on the horizontal. We have XL, the inductive reactance, as the horizontal. And then the hypotenuse of that is the total impedance, Z. Yep. And again, this angle in here will be the same as that angle there, always. Yep. So there are a range of calculations that you can do around this type of circuit where we've got an inductor and a resistor in series. So let's have a look at that little circuit there as an example. We've got 10 volts at 60 Hertz, and we've got 5 ohms and 10 millihenries. No, that's an inductor. 10 millihenries, was it? Okay. Yeah. So total impedance. We've got this triangle here, and we know this. That's 5 ohms. What's XL equal to? Two pi FL. 2 pi times the frequency 60 times the inductance 10 times 10 to the minus 3 equals. Ohms. Is that properly rounded to 3 significant figures? Yeah. How can I now find Z? It's minus 3. Yeah. Ohms. Right. How can I fully, what do I need to do to fully describe Z? Yeah. So we need to find this angle in here. I'll call it alpha. Tan of the angle is equal to XL over R. So what's L equal, alpha equal to? Therefore, alpha equals tan to the minus 1 of XL over R. Tan minus 1 of, what was XL? 3.77 over 5 equals I'll have it in degrees, please. Therefore, ZT is equal to 6.26 ohms angle 37 degrees. So that's finding the impedance total. Okay. Well, if you've got an impedance that's not at 0, which is a resistor, then you aren't fully describing it if it doesn't include the angle. Yeah. Okay. Current I in this circuit. Yeah. How do we calculate I? Change that a little bit. Yeah, and you've not been given an angle, so you have to assume 0. Yeah. And how do we do that? Which equals? What, 4.46 is in 10?
Oh, hang on.
1.68 amps angle. Does that work with civil? Current lags voltage? No? I haven't said you've got to do anything for the assignment. Where's the assignment coming? So, calculate the current in there. 1.68 amps, angle 37 degrees. What I just want you to think about is, how would that current change if I changed the frequency? If I doubled the frequency, what would happen to the current? Look through those calculations, double the frequency, what happens? To that first calculation. That becomes twice as big. Okay, so look at the triangle and think this line becomes twice as long if that was drawn to scale. What happens to Z? It's going to get bigger. Yeah? So, and the angle's going to increase. Yeah? So what happens to the current if the magnitude of Z has got bigger and the angle's increased. Assuming the voltage stays the same. Current will be smaller. Yeah? And more out of phase. So as we increase frequency on an inductor circuit, the inductive reactance gets bigger, the current decreases. Yeah? Consequently, if I halve the current, what happens? Yeah, the inductive reactance would halve. Therefore, that line would be half a length. The angle would decrease. It's the opposite effect. Okay? I just want you to be aware that this module not just about calculation, it's about understanding the underlying principles. Okay, so let's just put a note about that. If frequency is doubled, if frequency is half of it, what we done last week is already there. So I'll just call this one update and date it today and put it with it. Alright? If frequency is doubled, then XL will double. ZT will increase. Don't think it doubles, because it doesn't. Yeah, but it's going to increase. And angle increases. Therefore, increased frequency means current will fall. Opposite is true if frequency reduced. Okay? Yeah. And it's really important to understand those underlying principles. Really helps with the maths. Think, you can think then, does my calculation, when I make a change to the circuit, does my calculation look right according to the principles of what's changed? And we're talking here about changing frequency. Yep. So we haven't changed any value in the circuit. All we've done is change the frequency of the supply, and the conditions change if there's reactive components involved. In this case, an inductor. Yep. So, moving on yet again. The RC series circuit. In this circuit, again we're applying the fact that the current is true to both. So we put that as an in-phase component, and it's in phase with the resistor voltage. And then we've applied the capacitor voltage being 90 degrees behind the current. Yeah. And we've ended up with the total voltage being this phasor here as a parallelogram of the other two. Alright? And we end up with a voltage and a current that are out of phase from each other by this angle alpha again in here, but it's a negative angle because it's down below the zero line. Okay, it's most common to do angles between 0 and plus 180 degrees clockwise, anti-clockwise as being positive, 0 and minus 180 degrees for the angles between clockwise from zero. Alright? So again, we can do a range of calculations. we can look at this triangle here of voltages. So we've got ER, EC, and ET. There's an angle in there. And I know the angle in the other diagram, steeper, but still significantly. So we've got a voltage triangle, okay. And then we can have an impedance triangle. Where we've got R on the horizontal, XC minus 90 degrees, Z with an angle alpha in there. Yeah. Okay. And that's, we'd express the angle as being negative. So that's going clockwise around from 0. Yep. If we take our circuit again, component values this time are 5 ohms and 100 microfarads. Same voltage and frequency. So we've got 5 ohms, 100 microfarads, 10 volts, 60 hertz. This in here, this XC is equal to 1 over 2 pi FC. Yep. So total impedance we could calculate. Again, let's draw this triangle. 5 ohms. For consistency, I ought to draw it the other way up. Five ohms, XC there, Z there, angle alpha there. XC, 1 over 2 pi, FC, 1 over 2 pi times 60 times 100 10 to the minus 6. 26.5 ohms. Yep. So Lewis, ZT is, and we get that. Pythagoras theorem, square root of r squared plus xc squared. Root 5 squared plus 26.5 squared equals 79.3. Therefore, ZT is equal to 26.5, oh, hang on, 5 ohms into 5 ohms angle 26.97, sorry, ohms angle minus 79.3 degrees. You have to remember that that's negative when you're doing the calculations by hand. Current. I is equal to V over Z, 10 angle 0 over 26.97 angle minus 79.3 degrees equals 10 over 26.97 must be somewhere about 0.2, 0. What? Amps, angle 79.3 degrees. Does that fit with civil? Capacitive circuit, current leads voltage. Yeah. Head of positive with respect to that other voltage. Okay? So that's an inductive circuit. Right. What happens here if I double the frequency? What happens to XC? What I'm trying to ascertain from you. Think in terms of what happens to XC if I increase F, if I double it, make it 120. If I make F 120 instead of 60, what's going to happen to the value of XC? Smaller. I'm glad you didn't say half, because it won't be half, right? But it will be smaller. Yeah. So if XC gets smaller, right, what happens to Z? This line gets smaller. What happens to Z? It gets smaller. What happens to the angle? Decreases. Yeah. So where increasing frequency with an inductor, lengthen the Z line and increase the angle, increasing frequency of the capacitor does the opposite. Yeah. So if we increase frequency, XC will get bigger, therefore Z will get bigger, and its phase angle will get smaller. So if Z's magnitude gets smaller, what happens to the current? Increase. So the point I'm making is these two components, inductor and capacitor, work opposite to each other. So if you've got both in a circuit, which we're coming up to in a minute, yeah, one will cancel some of the other 1A to give an overall result. Yeah. So a circuit can be, that's got both components in, can be overall capacitive or overall inductive, dependent on which reactance is bigger, as you're going to see in a minute. So I'll put a statement like we did for the other one. If frequency is increased XC will decrease ZT will decrease and its angle will decrease. Therefore, the current will increase. Note, this is opposite with the effect on an inductor in the same circuit. Okay. If you just to clarify that opposite action in high power systems, so supplies to big factories, really high inductive loads, transformers, motors, welders, etc., cause the issue with current and voltage being out of phase with each other. I'm not going to explain why, but what it means is you have to supply more current overall through the cables to deliver the same amount of real power in watts to those loads. So if you've got, that would mean the supply authority there would say you've got poor power factor. And again, I'm not going to go into detail about that. But the way that they penalise you for that, because that means their cables have to be bigger. They can't transmit so much power if you've got poor power factor. So what they do to get round that is they add some capacitance into the circuit to bring that angle back in and improve the situation. It's called power factor correction. If you study this to level 6, we'll talk a lot about that in the level 6 electrical module. Okay. So just to give you, there is a flavour to this. The other thing is next year you will, in electrical principles, make and test, analyse some filter circuits that use this fact of inductors work in one way, capacitors work in the other, to filter out certain frequencies from a circuit. So you'll make a band pass filter, a low pass or a high pass filter. All right. So there are a variety of uses of the fact that these capacitors and inductors work opposite direction to each other as frequency changes. All right. So let's have a look then at a circuit where both are involved. Okay. What happens is we've got a current I in our phasor diagram there in phase, and a VR there. So there's I, and then what we have is the inductor voltage plus 90 degrees, and it's I times XL. And we've got the capacitor voltage in there, okay, and then we can have resultants of both of those, and I'll show you that a little bit better in a minute, because these two work, as we said, opposite to each other. Okay, so I'm going to put that on another page. So it is, if we've got R, L, and C, and let's just think a minute about the total impedance. Yeah. There's R on the horizontal. Yeah. And for the time being, I'm going to assume, let's put that as R, L, C. Assume XL is greater than XC in this case. Yeah. So then we'll have an XL, horizontally, it's 90 degrees positive to that. Okay. We'll have an XC, and I've assumed that it's less than XL, 90 degrees negative. Alright. Now, the resultant reactance, the overall reactance, X, is the difference between these two lines, and because XL is bigger, it's up there. So what we've got here is, and it's always XL minus XC. So obviously, if XL is bigger than XC, that's going to be a positive value and go upwards. If XC is bigger, it's going to be negative, and it's going to go downwards. All happy with that? Yeah. So our resultant then, run out of colours, our resultant comes in across there. Take the combination of the two reactances, take them across there and make a parallelogram with the resistance. There is our actual impedance, ZT. The circuit contains both an inductor and a capacitor, but going by the angle, that's inductive overall. So that would give us a lag and current. Yeah. If I change something in the circuit so that XC becomes bigger than XL, then that will come down below the line, and overall the circuit would be capacitive despite having both components. Yeah. So, if you think about it, increase in frequency in this circuit would mean that bigger XL, and this value, and ZT would increase. Decrease in frequency would see XL get smaller, but XC get larger. Eventually, resultant phasor into the negative side and making the circuit overall capacitive. So you can't tell until you know which one of the two, XL or XC, is bigger, as to whether that circuit is overall inductive in nature or overall capacitive. Yeah. So let's have a look at one with some values, shall we? we'll use the same three values as we had before. And we'll use 10 volts at 60 hertz. How can we, the magnitude of that will equal, we need to find, from the previous questions, XL was, if you look back at the circuit with just an inductor in it, yeah. Just give me the answer. 6 point something, wasn't it? That's quick. 3.77 ohms. XC 1/2 pi FC equals, that was 29 something, wasn't it? Yep. So what we've got is this. Let's draw it out. Get rid of that for a minute. We've got the R here, 5. We've got 3.77 XL. It's not scale. We've got 26.5 for XC. So X here is 26.5 minus 3.77. And our Z is in there, and there's the angle. Get well on there, yeah? So Z total is equal to square root of R squared plus XL minus XC all squared. Follow that, yeah? Plus square root of 5 squared plus 3.77 minus 26.5 all squared. So that is less than the overall magnitude of the impedance when we had just the capacitor in, which is what you would expect, because that little bit of inductance is pulling this up here and shortening that length of that line, and we'd expect it to narrow the angle. And alpha, 10 to the minus 1 of XL minus XC. I'm putting this in here like this so you know where it all comes from. Over that, over R. 10 to the minus 1 of 3.77 minus 36.5 all over 5 equals. Yeah, because doing that like that is going to make that negative, and therefore your angle's going to come out negative when you put it in the tangent button you calculate. Quite handy doing it that way. Work out that figure. That's why I said you must always do XL minus XC. So if correctly get the negative angle that you calculate. Alright, and is that angle less than what it was when we had the capacitor without the inductor? 79, so it's reduced that angle by 2.3 degrees. Not much, but considerably smaller than the reactance to the capacitor. Alright. Don't generally find, particularly power circuits, where the capacitive reactance is the higher. It's usually inductive loads like motors and transformers make a quite high inductive reactance that needs correcting with capacitance. Okay, so our current I our overall impedance, by the way, ZT is this 23.27 ohms angle minus 77.6 degrees. And we know the capacitance is bigger, so that looks right. Got a negative angle, and our current is V of a Z 10 angle 0 divided by 23.27 angle minus 77.6 equals. And that should be slightly higher than it was because we didn't have the inductor in there. Amps angle plus 77.6 degrees. Does that work with civil? Overall capacitive, current leads voltage? Yeah. Alright, worthwhile check.